Hi, we're back in section 3. In this section, you will learn the design steps of operational amplifier. Let's begin. Let's do some recap on full custom design flow. There are four main steps. The first one is design specification. The second one, we will design the schematic circuit. And then we will proceed with simulations. Once we get the result from the simulation, we will check whether the design meet the spec. If it's not, we will fine-tune or redesign the schematic again. This loop will be repeated until the specification is satisfied. Let's begin the design steps. The first steps is to determine the initially channel length L to be used for the design. This is a key parameter that affects the performance and characteristics of the circuit being designed. The channel length is a technology-dependent factor that needs to be carefully selected. The channel length is a critical design parameter that directly impacts the speed, power consumption, noise performance, and scalability of a circuit. Careful optimizations of the channel length is crucial to achieve the desired trade-offs and meet the specific requirements of the application. The second one, determine the compensation capacitor CC to achieve the desired phase margin. The compensation capacitor is crucial for ensuring the stability and proper operation of the circuit, particularly in feedback system. The phase margin is a measure of this stability. The formula provided, Cc greater than 0.22 of Cl, indicates the relationship between the compensation capacitor and the load capacitance Cl. So Cc is designed to be proportional to the load capacitance Cl with a coefficient of at least 0.22. This relationship ensures that the phase margin is maintained within the desired range. Proper selection and tuning of a CC is essential for ensuring the reliable and the robustness of the operation uh, of the design system. The third one, determine the tail current based on the desired slew rate. The tail current is an important design parameter that impacts the speed and dynamic response of the circuit. The slew rate is a measure of how quickly the circuit can change its output in response to the changes at the input. So the equation given here is the slew rate times with CC. The fourth one, determine the transconductance GM1. Uh, the input differential pair on the based on the desired gain bandwidth GBW and the compensation capacitor CC. The transconductance is a measure of the current voltage relationship of the transistor in the input stage, and it directly affects the overall gain and bandwidth of the circuit. Let's continue with step 5. Step 5, we determine the aspect ratio W over L. W is width, L is the channel length of the differential pair transistors M1 and M2. The formula provided shows that the aspect ratio is determined based on the transconductance Gm, the transistor parameter mu n cox, and the tail current IDS. So there are few implications of a poor aspect ratio selections. The first one, an incorrect aspect ratio can lead to suboptimal transconductance, resulting in lower gain and reduced high frequency performance. The second one, poorly chosen aspect ratio can cause the ICMR to be too narrow and shift outside the acceptable range, limiting the input signal handling capabilities of the circuit. The third one, An incorrect aspect ratio can lead to higher power dissipation, as transistor may not be operating at their optimal efficiency point. The improper aspect ratio selection can lead to increased Miller effect, ringing, and other undesirable behavior, compromising the overall circuit stability and noise immunity. So the formula here given by GM1 squared over mu NCOX times with IDS. Okay, and then the step number 6, determine the aspect ratio W over L width and length of the transistor M3 and M4 to achieve a positive ICMR. So the formula here is more complex, involving the drain current, the transistor parameters, mu P, COX, VDD, ICMR, and VGS max. Okay, voltage gate to source, and the aspect ratio. So these aspect ratio calculations are crucial design decisions that impact the overall performance and characteristics of the circuit. The proper selection of the transistor dimensions as defined by the aspect ratio is necessary to meet the desired specification and ensure the circuit's optimal operations. Okay. So far, we have seen 6 design steps. These parameters are all interrelated and need to be carefully balanced to achieve the desired performance characteristics of the circuits being designed. The formula provided represent the mathematical relationships between these design parameters, which allowing the circuit designer to determine the appropriate transistor sizes to achieve the desired functionality. Okay, in this page shows 2 more additional steps in the design process. Okay, focusing on the determinations of the saturation voltage and the aspect ratio for the transistor M5. Okay, which is the tail current that's flow through. Okay. Steps number 7, determine the saturation voltage of transistor M5 using negative ICMR. The formula provided shows the calculation to find the saturation voltage VD set based on the input common mode range ICMR and the drain current IDS, the transistor parameters mu n COX, and the maximum gate source voltage VGS max. Okay, and step number 8, we determine the aspect ratio W over L of the transistor M5. The formula here calculates the aspect ratio based on the drain current IDS, the transistor parameter mu NCOX, and the saturation voltage VD set determined in the previous step. Okay, so these calculations are crucial in ensuring the proper biasing and operation of the transistor M5 within the circuit. So the saturation voltage determines the headroom available for the signal swing, while the aspect ratio affects the current handling capability and other performances characteristics of the transistor. So careful selection of these design parameters based on the circuit requirements and constraints is essential for achieving the desired overall circuit performance and functionality. So at this point, we already covered all steps that we need to learn. I'll see you in the next section where we do one by one calculations um, that we need to do in order to design an operational amplifier.